Um, well, great. This week I am speaking with Dr. Hyemin Yoo, and we are going to be discussing her dissertation thesis, The Sine Condition Test Plus Development of a Novel Alignment Method Using Deflectometry and the Sine Condition Test. We're going to get into this. It's a topic that's particularly interesting to me. I have background in deflectometry, I've dealt with alignment. The paper itself is a very interesting application of combining the sine test for off-axis alignment parameters and deflectometry for on-axis alignment. And it provides a really elegant and accurate way to align systems. But before we get into that, I want to hear a little bit more about how you got in optics in the first place.
Okay. So I used to study astronomy, and more specifically, radio astronomy, dealing with very long baseline interferometer. And then the goal of that was to image active nuclei or active galactic nuclei in the space. And then I had to analyze how fast the jets coming out of the AGN emitted. And then dealing with such like extreme science, this concept of VLBI, like supporting high spatial frequency by having two antenna separated really far and of providing us like resolution that well. I mean, it was interesting for me. I mean, actually, so my goal, like my job was to like analyze the raw data from VLBI, but I figured I was more interested in the instrument. I wanted to know like basic principles of how they actually do like imaging with the antennas. Right.
And sorry to interrupt you. This was during your undergraduate studies. Is that accurate?
Oh, so actually I have another master's degree in astronomy. So after graduated as undergrad, I joined grad school in South Korea, Yonsei University. And then that was how I started studying radio astronomy using VLBI. And then this concept was very interesting to me, but unfortunately, there was no place that I could learn about this instrument principle. Like I was more focused on the science part, but I always wanted to know why this UV plot matters. So UV plot is simply it shows which spatial frequency this interferometer baseline could resolve. But like I couldn't really understand back then, like why do they care about covering UV plot as much as they can, and what does it mean? I mean, they say it's better if it's like filled with the dots better on the UV plot, but okay, I just accept it and move on to like analyzing all the raw data. But I was more into this, like why does it matter? I mean, why can't we do imaging with antennas? And
right.
So I kind of decided to change my major. That was the point. I mean, I still like try to apply for like PhD program in the US for majoring astronomy. But at the same time, I had this like doubt that do I really want to continue astronomy? Don't I more want to learn about like instruments better? That was my, that was my concern. I mean, what would happen if I continue things that I don't like? And maybe it's a chance to find something that I'm more interested in, I really am interested in. And that was the moment like that I sent an email to their work. So there
Ah,
was in like Tucson teaching optics at U of A, like our grad school.
hmm.
And then I knew him because he also studied at Yonsei University, that my undergrad like was there. And then every he's actually very legendary at Yonsei University. And when I like told people that I have this like thoughts and I'm not sure if I really want to change it or not, and then someone asked like recommended me to contact him. And then I wrote an email. And then usually Daewoo is a very busy man, right? But luckily, he was at the airport, and I guess like the plane was delayed or something. So he opened up his laptop to see, like, read emails, and my email was on the top. And then he
Ah,
clicked it, and then he read my email, and he got so interested in my background, and then, oh, we got to see each other. I mean, I'm going to Korea right now. We got to see each other. And almost like 2 days or 3 days, he showed up she showed up at the same university. And then we had like discussion about like 3 hours about like my research on like VLBI. And then he gave me some good like stories about U of A. What about learning? How is it like learning optics that he really enjoyed? I mean, he also studied astronomy before and switched to optics. And then he's now teaching optics. And so it was like a very, very valuable conversation. I mean, yeah. And then I didn't really ask him for recommendation even because I thought he might be, very busy and popular guy that everyone would like to have a recommendation letter from him. So I thought maybe I should find someone else or something. But he was the one who actually brought that up. I mean, that he was willing to write me a recommendation letter to U of A. And then I was like, oh, thank you. And then eventually I was lucky. And then, yeah, I got the admission for master's program first. Actually, I applied for a PhD, but it was really, popular program. Then they only offered me master's, but I thought I could still like take it as a chance to learn new things. So that's how I started optics. It went so long story, but yeah,
and
that's how I started. Mhm.
did uh I guess at this point, hopefully it's a fair point to make an assessment. Was it the right decision? Do you think are you happy that you made that switch?
So for now, now that I'm done with done with graduate program, I say it was the right choice. But um, when I first started, I mean, when I landed in the middle of the desert in Tucson, I wasn't really sure. I mean, like seeing all other students looking very passionate about optics, but I kind of had this experience from astronomy that I can always make choices that that I may like say that I didn't like it later, like astronomy. I mean, I'm not saying that I didn't like it, but there could have been a better choice always. So even for optics, even if I decided to studying new major, based on my like feelings on instruments, I still had some doubt. Like, would I be really good at it, or would I be able to say that I really like it? It's like I was hesitating to say that optics is my thing. I mean, just I wanted to see if I'm really good at it, and it took me um, I mean, yeah. So it's a complicated feeling. I mean, I like it, but sometimes I suffer a lot. And then it brings me another emotion that's like conflicting in me. And that was what I was like before when I just started studying optics. And also I started as master's student. So and I wasn't sure if I could switch to PhD later because it's hard to no, it's kind of competitive as a master student from a foreign country. It was really hard to get admission for the same grad school as like switching from master's to PhD. It
Mm-hmm.
wasn't like easy process. So I was like very confused, and also I had to like deal with this new environment, and also using English was not as easy for me as a yeah. I used to live in US with my dad for 1 year, but that was really long time ago, so I almost forgot how to use English.
Mm-hmm.
So and everything was so stressful. So it took me so long to finally say it out loud that I like optics.
Yeah.
Yeah. So
Yeah,
that's my true story, actually,
I, I
to being
think that,
honest.
you know, for most people, um, certainly you talk to some people who say like, oh, well, I always knew that I really liked optics and I still really like optics. But I think for most people going through graduate school, um, probably in any field, but certainly in optics, it's not very fun to start out with. It's really
Yeah.
stressful. It's really hard. And from what you're saying, yours was, and I think this is probably a commonality for foreign students, is yours was about as big of a change as you could have on top of the stress of grad school, on top of the stress of can I go, is it the right decision because I'm in the master's program and I want to do the PhD, and that's not easy. So a lot of confounding factors, um, but I'm very glad that you like optics now, and I think
Yeah.
this makes a nice transition to your dissertation. So for the listeners, I mean, I've known you for a bit of time, and I ran into you several months ago, and you're saying that you were about to graduate. So I was really excited,
Yeah.
and I knew there was a little bit in deflectometry, and I bothered you. Can I interview you? And can you send the dissertation? Um, so the dissertation was spectacular. Like I truly mean this
Thank you.
for any listeners. I think this is something worth reading if you're in the field of optical testing or alignment, or if you're interested in it. Um, your thesis is like phenomenally well written, and it provides a really great intro, and a very good approach to, I think, explaining some of the more complex topics. But before we get to that, I think you actually hit upon this feeling of you understand it well now. You have this sentence right in the intro that says, I quote, "Lastly, I want to thank my advisor, Dr. Matthew Dubin, especially
Yeah.
for spending approximately 700 hours discussing optics with me. I
Yeah.
had doubts about myself for the first few years in Tucson. Then, at some point, I figured the doubts were gone. Instead, they were replaced with great confidence." I think that's really the goal of a PhD program, right? That you go in, you don't know it, but you end hopefully feeling confident in your domain. So I really like that few sentences there at the beginning.
Thank
Um,
you.
so uh, I do think that your dissertation was very well written. As people probably are familiar with, dissertations are fairly dense, and I'm even familiar with this field. But I took notes, and I have several pages of notes. But I think that my takeaway was the general claim is, it's pretty hard to optically align systems, and you make this caveat of optical alignment, um, and that what you found in your work was, if you combine the sign test and deflectometry, then you can capture common misalignment modes. And I'm kind of talking around it because we'll get into the details, and you can do so in a convenient way.
Hmm.
So, um, I guess, is that a good summary? And I kind of want to start from the beginning and go through it. So is that a good summary to begin with?
Yeah, I think it's like a summary. Yep.
Okay, perfect. I got the summary right at least. Um, So one of your first claims is, optical alignment is aligning optics to achieve imaging performance over a full field of view. And there's a bunch of methods to do this, right? There's CMMs, profilometers, optical alignment methods, and you make this distinction about optical alignment methods. So can you describe what you mean by that a little bit?
Okay, so usually when we think about alignment, it's just in most cases we think about it as mechanical way of aligning them, optical elements. Like you could do some good, fabrication for lens cells or the structure, or like you can use some like cool methods like CMM or laser trackers to bring your optics to their ideal locations. So these are all mechanical alignment. And what's behind that is actually you expect to get good optical performance after performing mechanical alignment by controlling their tolerances. So actually, we don't do any like measurement like during the alignment. So we don't know if the optical performance at the whole field of view of this optical system will be good or not. I mean, we just like do some tolerance analysis before we actually do this like choose alignment methodologies, and then we know, oh, like within this range of tolerances we will like have 99.9% chance of having good optical performance over the field of view. So that's usually how we do alignment. But when I say optical alignment, I specifically meaning something that we actually do measurement during alignment. So we have to know the optical performance over the field of view while we do alignment. So it's going to be measurement and alignment, measurement, alignment, back and forth, back and forth. It has to be like that for optical alignment. And to do that, for optical performance, like I said, it's what matters is having good optical image quality over the field of view, not just at the center of the field. We have to know that it will be good for all the field points over the sensor that we like measure like something like object. To do that, in typical methodologies like interferometry method or some other like cool method that I mentioned in my dissertation, like that's used in JWST. They use phase retrieval, and like, but they still have to move their measuring instrument to multiple field points to see if their alignment status gives you good optical performance over the field of view. That's actually very difficult. I mean, moving your optical like instrument that measuring like optical performance and knowing their locations correctly is the problem. I mean,
and I think we should give context here. So
okay,
how good the JWST
yeah,
is going to be one end of the spectrum example,
right.
but how good do we mean when we're talking about alignment? I mean, I think the audience knows if we're talking about the James Webb Space Telescope, okay, it's for telescopes, right? And these tend to be really good systems. So how well do we need to align them? And I recognize that this depends on the tolerance, and I think you're about to get into this, so I apologize for interrupting you, but how does that then translate to how well you're moving your instrument, right? I think that's a
Right.
really important connection of how accurate we're doing some of these things.
Okay. Please correct me if I'm wrong. Like maybe I misunderstood your point, but I guess you're asking like what type of aberration we care, like in the misalignment.
Yeah, and yeah, exactly. What type of aberration and and I guess another way to say it is a lot of these systems you require really good performance, right? Even out at the edge of the field of view. I'll give a counterexample that I'm familiar with. Um, I've been familiar with a telescope system that's going, or an imaging system rather, that's going to be that needed to test the distortion across the full field of view, and it needed to test the off-axis wavefront aberrations as well. And what that ended up requiring in one modality, right, with a autocalling telescope, was positioning the position and the angular input of this thing to like an incredibly insane tight mechanical tolerance. Like submicron, super accurate angular testing, and it's not and in this for this system, it's not the JWST, right? They can't spend however much money making a perfect system to position their input. So, anyways, I interrupted you, but I just wanted to give context that a lot of times to get these accurate, you have to position your device so well, and it's really time consuming, really tedious. So
Right. So yeah. So usually, the thing that degrades the optical like performance, like image quality over the field of view, we call them like aberrations, like different aberrations. Of course, there are various kinds of aberrations, but there are specific aberration terms that directly related to like misalignment in the system. So what I'm talking about here is, do we have ability to measure those aberrations, like misalignment aberrations that degrades the image quality? So if we go into more detail, like the MTF curve, like modulation transfer function, that's what we use as a metric to understand the image quality at specific spatial frequency that this optical system can resolve. But usually existence of unwanted aberration will like degrade the shape of the MTF curve, and therefore we will not have good optical performance at over the field of view. So it depends on like, so I cannot say, I cannot tell numbers specifically for how much like perturbation are we talking about, because it depends on what your system is. Like, does your system works at like visible light or infrared, or does your system care about like high spatial frequency object or low spatial frequency object? That determines the tolerances in aligning your optical components. So it depends. I mean, of course, extreme system like JWST or any like lithography optical system, like those definitely requires like very good alignment. I mean, for those, perturbation, maybe within like a few micron or something. So, but that numbers are determined from basically this MTF curve, like how well do you want to resolve your object? Um, and then, so I don't specifically say numbers in my dissertation. That's the reason why I don't have that numbers for anything, because it depends. Your system depends on what you want to see, what type of system you have. So that's why I only talk about this 5 misalignment aberrations that I like specifically mentioned in my introduction. That these are all goal to have good optical performance. You have to know these 5 misalignment aberration that's induced by misalignment, and by knowing how to perturb your optical components, you can reduce the amount of 5 misalignment aberration you have in your current system. And then eventually, like there's a matrix linear, like a relationship between perturbation and amount of misalignment aberration you have. So eventually you can calculate how much perturbation you should add to different degrees of freedom of each optical elements. So that's the flow. I mean, I introduced 5 misalignment aberrations so specifically because that's my goal. I mean, my methodology, the Sine Condition Test Plus, SCT Plus, aims to measure those 5 misalignment aberration correctly.
And
So,
why did you choose those five? And
um,
yeah,
so there is a mathematical reason. Actually, it's not that I
yeah.
choose whatever I want, of course. So the resources, I mean, the thing that causing the 5 misalignment aberrations that I refer in my dissertation, those are caused by sidal aberrations, like typical sidal aberrations that exist in rotationally symmetric systems. Like defocus, spherical, field curvature, like sidal astigmatism, sidal coma, those major things. One of the textbook written by Professor Mahajan, he talks about how these sidal aberrations and perturbation, like tilt and decenter of optical surface, can cause this 5 misalignment aberration. So actually, there are more terms, but I only choose to deal with 5 aberrations because these specific 5 terms show linear relationship with the degrees of freedom in your system. So till like let's say I decentered 1 millimeter, I'm having like half wave of I don't know linear astigmatism. If
Mhm.
I decenter by 2 millimeter, then I know that it's going to be twice the magnitude that it used to be. So the choosing those terms um, can help me to build a sensitivity matrix. So that gives you like linear relationship between the perturbations in the system and the 5 misalignment aberration. That helps you to find out the right solution of how to perturb your system. So that's the reason why I'm specifically talking about 5 misalignment aberration. Of course, there are other like misalignment aberration terms that are like high order terms, obviously. But that thing is unfortunately not solvable with my methodology. But the good thing about it is that these 5 are the most, no, like except for boresight error, magnification error, these 5 are the most like lowest aberration that you can think of that's caused by misalignment. So usually if you correct them, the other higher order terms will also be corrected together because they're all coming from the same, sidal aberration existing in, like ideal, like nominal design. So that was the logic. I mean, the 5 misalignment aberrations are decided like that.
And again, I want to reiterate to anyone listening or watching that I assume that I'm pretty sure that the dissertations are just publicly accessible.
It's not actually accessible yet
Oh, okay.
because,
Well,
well, I've been working on writing journal article. So uh, I've asked for embargo public
yeah.
statement. So yeah, so
Well,
maybe not yet.
when it is accessible, we will
Yeah.
retroactively for sure put a link to your to the dissertation and or the papers, whatever comes first. We'll
Mhm.
also link to Dr. Mahajan's book. But your intro where you kind of describe the theory of it is a really great resource. I mean, it's written really well, and um, and you kind of you expound upon as well that we enter um, we enter into this null space, right? Where if we only have on-axis field points, then there's some degeneracy that we can resolve by using off-axis field points. So I just want to mention that. So you started to go into it, but you transfer from okay, well, if I have a system, I have lenses or I have mirrors, and I misalign one to the other, obviously, maybe I'll take a step back. Obviously, you design a system in your optical design software and it's perfect, and you're going to order these lenses, you'll type it in and send it to someone, and they'll send you these floating lenses in free space, and they'll all be perfect, right? Oh, of course not. That can't happen. It never happens. I think you have a quote in your early in your dissertation of you never get actual ideal lenses. So they'll have some errors. And like you said, when you position them, that positioning will have some error. And you've created this misalignment matrix. You have your design, so you can make your misalignment matrix, and you know if I shift lens two relative to lens one in decenter or spacing or possibly clocking, and this will kind of be relevant in a second, I'll get some unique systematic misalignment mode of these five modes that you're discussing, and you can analyze it in some way. And so you transition to talking about the Abbe Sine condition, which was, I think, from Ernst Abbe. And at least for me, this was like this cool topic that you kind of heard about in optics, but you didn't. You know, I'm not speaking only for me, not for other people in optics. It was like, I don't really get it. I don't really know what it means. And you would ask people and they'd say like, oh, well, it means that it obeys the Sine condition. It's like, well, okay, that's kind of circular logic here. But so can you kind of explain what the original form was of what Ernst Abbe came up with, and maybe how you utilize the expanded form or the generalized form?
Okay. So Sine condition was a revolutionary method to design a lens without sidal coma. So a long time ago, when we had no modern computer, obviously the lens designer, they had to do hand drawing to do all the ray tracing for different field points to make sure your rays end up being a point source on your image plane. Otherwise, that means you have like sidal coma, and they didn't want that. I mean, but it's a time-consuming way of designing thing. Like that it's not going to converge to like different field point. Then you have to like change the radius of curvature again and see if it trace it again and make sure that it converge to a point. That's really time-consuming and very tedious way of like designing lens. Probably, I can imagine. So Ernest Abbe, like he was the one who come up with the Sine condition. This is the condition that your optic should satisfy to make sure that your optic doesn't have sidal coma. So sidal coma meaning linearly field dependent coma. And this is revolutionary because by only tracing on axis, right, you know how the performance will be at off axis. That's crazy. I mean, usually you have to move your like optical device or whatever to the field point that you want to know the optical performance of that like optic. But Abbe like suggested, oh, make sure your ray on axis satisfies Sine condition. Then your optic will have good optical performance at off-axis field point. You don't have to do all the handwriting, ray tracing for off-axis rays. Yeah. So that was why it was revolutionary, I mean, back then. And probably that's why our professors at U of A, they like briefly mentioned during like classes because it is really important. But unfortunately, these days, people could use like, great computing power to design all the optics, and they started to like forget about this cool thing. But probably professors, they still want to, mention this because it's so cool. And then, yeah, and the good thing about the like Sine condition, like specifically Abbe condition, is for it was developed for dealing with sidal coma, but in general, like Sine condition can be applied to any linear field dependent aberrations, like linear astigmatism, linear focus. those are two major misalignment aberrations that are linearly field dependent, and that we can measure with the Sine condition. I mean, we can deal with them with Sine condition, but again, it hasn't been really adapted to the field because we have cool computing power, and then they can deal with this problem with other methodology like interferometer. Like conventionally, people trust interferometer because it's quite guaranteed, right? Well, compared to other methodologies, when
Yeah.
yeah. So but the Jim Burge and my advisor Matt Dubin, and also the work of Dr. Sarah Lampen, they worked on this Sine condition test. So they are adopting Sine condition to measure linearly field dependent aberration in misaligned system. And then they published paper about it that it does measure linearly field dependent aberration pretty well, like linear astigmatism and linear focus. So but that's the flow. I mean, so Abbas started Sine condition for designing optic that's good for good over the field of view, good image quality over the field of view, but it can be applied to misalignment problem because major aberrations from misalignment are linear astigmatism and linear focus. So Matt, Burge, Jim Burge, and Sarah, they came up with this concept of testing the Sine condition, so they know how much aberration, linear aberration, you will have in your current system. So that's how it went. I mean, of course, there were other publications related to Sine condition to deal with various detailed problems. But so yeah, that's
those are the
understanding.
key points. Yeah.
Yeah. Key points to my dissertation.
Yeah. And so we'll include links to kind of all the papers that we're mentioning.
Mm-hmm.
And I think that in the original Abe paper, it's for rotationally symmetric systems, which is unsurprising when he wrote it. I think that you reference, I want to say Elazari came up with this generalized form. And so I think in that form, he's treating everything like vector components relative to some coordinate frame. And so the fallout, and correct me if I'm wrong, but the fallout from it was basically, if we're not violating the Sine, maybe that's the wrong way to phrase it. If we're obeying the Sine condition, then angular relations should stay consistent.
Right.
Is that okay?
For any systems, even for non-symmetric systems, if your system satisfies Sine condition, I mean, Sine condition can be different for different type of systems. Like, for example, finite to infinite conjugate system, you have to follow Sine condition that tells you the relationship between height and angle. And for finite system, you have to know the Sine condition for angle to angle. Such things some variation should be applied to your system. I mean, there's a specific Sine condition that you want to satisfy your system, that you have to make sure of that. But if you do that correctly, then basically you can apply this methodology to any kind of system to measure linearly field dependent performance.
Yeah, and the reason that I grimaced earlier when you mentioned interferometry is an interesting the time when it clicked for me of what the Sine condition means or why it's relevant is I had taken for granted that you buy an interferometer and you buy precision optics for it. It's interferometry, and precision transmission spheres do not always obey the Sine condition, and I think that's something that if you happen to be around a very fast transmission sphere, you can check this for yourself, and it should kind of click as to, oh, these rays that I
Yeah,
expect to all have equal
right.
spacing don't. Um, so yeah, I think that's a really powerful introduction and powerful reasoning for okay, the sign condition we through a lot of effort on various people, it's been generalized so that for even non-rotationally symmetric systems, even finite, infinite, finite, finite, etc., we have this form and we have this rule that's saying if I obey it, this is how things should look. You then transition into deflectometry. And of course, my very first note that I took was deflectometry is good. I think that's true. Um, you also suggested it's very sensitive to misalignment, particularly in low order misalignments. And um, and I guess so. Why? Just kind of briefly, can you, my background is using deflectometry for surface metrology, um, or maybe even, um, well, I'll leave it at that. It's surface metrology, and the misalignments were always a big headache. And
Yeah.
and in your paper, you looked at this and said, actually, this is really useful. And um, so can you explain why it's useful and also why you're mentioning this with the sign condition? How do they relate?
Okay. So I made a great deal about Sine Condition. I always get excited because it's the only method that I know of that can measure off-axis performance with on-axis measurement. Usually you have to be at off-axis to measure off-axis performance, but Sine Condition is not. But the truth is actually there are various versions of Sine Condition, but Abbe's Sine Condition, it assumes no on-axis aberration. So it only works when there's no on-axis aberration. Of course, there are like correction terms that you can add to Abbe's Sine Condition to like make it true for any kind of system that even having on-axis aberration. But for the simplest form of Sine Condition that you have some disadvantage in there. But that's why it actually wasn't being able to use for alignment purposes because there are three remaining misalignment aberrations: defocus, spherical, constant coma. These are on-axis aberrations. So if you don't know these three correctly, then you cannot like align your system well. Then I thought about it, and then Sine Condition and deflectometry both are based on like tracing rays. Actually, like if you know where your ray end up on your image plane and maybe surface on your optic, you can calculate their relation, and therefore you can calculate the slope and maybe the violation of the Sine Condition. So it's basically a very similar concept. So I wanted to see how I should merge them. Like if deflectometry can measure the part of on-axis aberration, then we don't have to worry about that when I apply Sine Condition to this measurement. So that thing that I come up with was to performing deflectometry at two monitor positions because deflectometry, of course, like I mentioned in my dissertation, is very sensitive to low order aberration. I mean, like geometric calibration is required to correctly measure low order aberrations, which is also defocus, spherical, and constant coma. Those are major like misalignment aberrations. But like deflectometry can be really good for relative measurement of the wavefront change, right? If you know how much change you apply to your instruments, like even if you didn't know the like absolute geometry of your camera and your monitor, if you know the change correctly, then you can measure the relative change. And that was the idea. I mean, by moving the monitor to right amount, like known amount, we can measure the change in the wavefront, and that's going to contain information about on-axis aberrations. And well, of course, it could be including some other things too, but because there's degeneracy, like for linear focus and defocus, the wavefront looks the same if you don't know your field point correctly. If you know the geometry where you place your camera, then you don't know if it's linear focus or defocus. But for now, it doesn't matter. It's what is important is that you performed like relative measurement to say this amount is defocus, and the rest of them will be linear focus, and that's going to be measured with the Sine condition test part. Because Sine condition test, if you have solved the degeneracy part, I mean, with deflectometry, confusing linear focus and defocus part, it can be resolved with deflectometry part. Then the rest will be treated as we only have linear focus in the rest of the data. And then we can create a matrix of like, oh, this is the amount of linear focus we have, this is the amount of defocus we have, and other 5, we can provide a complete solution for how much misalignment aberration we have. That was the flow, like that's the connection. We've been complaining about, there are some people complaining about, like deflectometry is awesome concept, but it's really sensitive and you need a like high precision geometrical calibration. So we only care about high spatial frequency wavefront errors, or there's like other studies that related to deflectometry is like, so okay, how do we improve this geometrical calibration? Is there a better way to deal with this problem? So it was like mainstream of like using deflectometry for high spatial frequency wavefront error, or let's find out what's the better way to do geometrical calibration. So, but I thought it in a like different way. Okay, this can be an advantage, like relative measurement. And for alignment purpose, it's not really important to know how much wavefront figure error you have. I mean, let's say you have spherical error on your optic. Well, like for telescope, 2-meter telescope system, you can adjust the spacing between two optics to compensate the amount of spherical aberration you have on your optic. Then you will eventually have good image quality over the field of view, right? So that's the point. I mean, of course, there's certain terms that I cannot correct with my methodology, like trefoil, it's something that you cannot correct with misalignment or perturbing your optic, but still, it can be useful still, like the methodology for alignment purpose, specifically for alignment purpose. So yeah, that was the idea, and my advisor and I really had lots of discussion, and there must be a solution. I don't know how I should approach with mathematical explanations. I wasn't sure about it, but we were pretty sure that there must be an analytical solution for alignment purpose if I can combine the Sine condition test and deflectometry. And then it took so many years to figure out every details. But anyway, yeah, we were so sure.
I do really like that you mentioned a lot. I mean, I really appreciate that you viewed what you said was historically seen as probably the biggest negative of deflectometry for absolute measurements of I don't know exactly where the camera pupil is. I don't know exactly where the monitor source is and whatever. And so I'm gonna get this error, and I like you said, either I won't worry about it, I'm only looking at high frequency, or I'll really spend a lot of time calibrating it. And you looked at it and said, oh, that's actually really useful. That's not a negative, that's an advantage. And I also really appreciate, and I think for any, I don't know if there are any, but for any undergraduate or graduate students listening, you've really captured the I think that the ethos of good graduate work, which is, I really think this should work. And I can't prove it all out yet, but we're going to prove it out. I'm pretty sure it'll work. And it takes, like you said, it takes, years or longer sometimes to get everything proved out. So I really like this method. You you basically do a deflectometry setup. Um, you expand it as well such that you could do this setup for a reflective system, so a more traditional deflectometry setup. And actually, let me add something here for listeners. Deflectometry, you typically have a camera, you have a source, and you're going to uh, display. You're going to emit light from your source at some known point. Rays will leave that. It'll hit a test optic. I say hit. I'm thinking about it still in the reflective case, and I'll just stick with that for the time being. It'll hit your reflective test optic, bounce off of it, and at some position on your source, the geometry will be right such that the ray will leave it, it'll hit your test optic, and it'll go into your camera. And you map your camera detector to your test optic, and you say, okay, well, this pixel corresponds to this region on my test optic. But you point out in your dissertation, it doesn't have to be reflective. It can be transmissive system, transmitting system. So it's a long way to summarize what you already said. I apologize, but basically you position your screen, you position your camera and your test systems in there some way, depends on if it's reflective or transmitting, and you capture a measurement, and then you shift your screen and you capture another measurement. And you note that the decenter when you shift doesn't matter too much. I'm assuming it can't be egregious, but a little bit of decenter is fine. How well do you have to measure that shift in your screen position?
Okay, so another good thing about my methodology is that it's really insensitive to this monitor position. So every time I explain my concept to the audience, they always say, "Oh, it's such a great concept. It looks good, but it looks like you have to like position monitor pretty well. I mean, you keep saying like you're shifting it the right amount, and then you know how much change you will have. But what happens if you like tilt your monitor on the way to when you're sliding it, or if you tilt it, that's gonna cause some error to your measurement. So the good thing about my
We
method,
all still have trauma from deflectometry. We thought, oh, this looks really great, everything's perfect. So now we know to ask this question. So sorry.
No, it's fine. I mean, because you know, like it can traumatize deflectometry people, like knowing the geometry of your optic. I mean, optic, camera, and monitor is really important. But my methodology, because I am, so I've been talking about this misalignment aberrations, but usually the way we interpret them is like wavefront, like in wavefront, like two-dimensional wavefront. But the way I deal with the misalignment in my methodology is actually in the vector field. So I use vector polynomials to describe how much like perturbation we have in the system. And we can, luckily, it's another work of Jim and Zhao. Actually, Chunyu works at AOM, right?
Yeah,
Right?
Jim and Chunyu, yeah.
Yeah.
I was very excited when I read your paper.
Yeah.
I went over to Chunyu and I said, someone wrote about the sine condition, and they referenced you a whole bunch, and he was excited. But yeah.
Oh, really? It's good to know. Yeah, so I was able to use their mathematical like polynomials to describe vector field, and then you can decompose them into orthogonal like terms. And if I choose the terms that are only related to misalignment aberration, the rest of them are like I don't care. It doesn't affect my measurement. It's nothing related to my measurements, so I don't care. Let's think about decenter, like decenter of the monitor. That's gonna cause error that's gonna look like all the vectors same magnitude in one direction. That term, I think it's like S2 and S3 or something, a combination of them. Those are not related to my terms. So there are only specific terms that I care. And these are like negligible because, I mean, I'll say irrelevant because they're not meaningful to my measurement. Of course, certain terms can be caused that are the terms that I'm interested. For example, like tilting it, it's gonna cause something look like S4, which is related to defocus. But the amount that caused by this tilt can be negligible, right? So in certain level, like that this amount of S4 is expected for my measurement, and this is amount that I want to like align. There are always tolerance behind this. So this is how well I want to align this telescope, and this is the amount of defocus I can tolerate, and that will like give you how much like tilt you can have on your monitor. If that number is negligible compared to what you truly care, then it's okay to have that perturbation. So that's the deal. I mean, of course, I cannot say for tilt, you can have as much as you want, never. But at least there's like logic. You can like think about it and there's a way to make your decision, like how much perturbation I can have on my monitor and such. And that is based on some mathematical explanation, not just experience. So it can be different for different telescopes with different performance requirement or something like that. So the goal of my paper is actually not giving them number, actually giving them a way to think about how to deal with this type of noise in your system or residual error in your system. And then, yeah, so that's how I put this.
I'm smiling because you've created a scenario where you'll be making future astronomy to optical scientists, students in the future, much like your story about the instrument, and if you have enough dots in the middle, it should be good enough, kind of convinced you to say, well, why? I can imagine that some student down the line will be saying, well, if you align it and the tilt's below this, it should be good enough. And they'll go, how come? I want to learn. So, okay. I mean, I'm already convinced. I was reading the paper at this point. I was already convinced this is great. But I'm not who matters. You have to actually prove that it works. So how did you demonstrate, that it actually works, and I guess how well does it work?
Right. So I guess that's the last part of my dissertation, so talking about experimental demonstration of SCT plus. So of course I wrote a paper about concept, and I did some simulation work in Zemax and MATLAB to show that how well we can align telescope with given amount of like figure error on your optic, or like given amount of like tolerance you would have, or given amount of like noise in your camera system or such things. So including all of that, it's still like aligned. It can still align your telescope by factor of, I always forget the number, but really good compared to what you have. Also, it can be better than interferometer for some cases because it has larger dynamic range. So I believe perturbation I added to that telescope model was 500 micron or something for the center and perturbation.
It was 500 micron. Yeah.
Yeah. So that is something that interferometer cannot measure because it has to be really close, and interferometer is only applied to fine alignment, not for coarse alignment. So that's the reason. But I'm showing that with this methodology, it's doable. But simulation is not good enough. Everyone wants to see experimental results. Introducing new concept to the field, it requires many responsibility actually. You have to provide concept, you have to provide some model to show that it works. And last thing will be probably it's an experimental demonstration. And that was the thing that my advisor, Matt, really emphasized when I was working on this. So I thought I was ready to graduate when I was done with the simulation part. Matt convinced me, you have to do experimental demonstration too. That's the complete set of dissertation that I want to see. And I was like, okay, let's do this. And dealing with this experimental demonstration, there are so many practical like details that you have to go like through. It's painful. Nothing is according to your plan. Everything is delayed. Everything is under your expectation, and you have to do this measurement over and over again until you find the problems. And then, okay, so back to the demonstration I did. What I had to do is to like show the performance of SCT plus compared with interferometric data. And also I wanted to show that I can predict the performance of the SCT plus with Zmax. So there are like Zmax modeling part and interferometer part, and lastly, the SCT plus part. So the important thing was to calibrate three different methodology. So if, let's say for Sine condition test, I'm claiming that I don't have to move the camera to measure the whole 5 misalignment aberration. But for interferometry method, I have to move interferometer or either, like the return optic to right field plane to like measure the alignment performance. The problem is that like if they are looking at different field plane, like let's say Sine condition test was looking at this plane, but let's say there was like return sphere for interferometry method. If you moved it along the wrong plane, then that means you measure your field dependent aberration at different field plane compared to the Sine condition test points. The most hard part about that was how to align them. I mean, how do we know if they're calibrated well? That was the problem. So I had to like come up with some custom designs to interchangeable like mount for camera and the return sphere, and also had to do so many months of like CMM measurement for knowing all the all the optic geometry, and it was painful. And actually, it's a side story, but I had to design custom a planetic doublet, like airspace doublet, to show this methodology. I mean, I cannot use telescope. I mean, it's not like it's lying around in the optics shop or anything. So I had to come up with that's compatible optical lens design. So I asked for custom design, and then unfortunately it was delivered with wrong spec. So, but it took me so long to figure out why my performance was not working, because it was hard to doubt that I got the wrong spec lenses. So I wasted 2 months and then another month to fabricate new lenses. They corrected my problem anyway, but that was very generous of them. I mean, they were really nice, and they supported my research. Actually, they gave me also discount because I'm a student, and so it was helpful. But for me, I mean, it's hard to doubt other people when you are graduate school, like low self-esteem, very low confidence. So like it's hard to like clearly say like it's not my fault or something. It takes time to convince yourself that it's not your fault.
It takes time to get there, right? Yeah.
Right. So and then I had to do the CMM measurement again. And another story is that I had to like visit Meteor Lab to do the CMM measurement. So I was like, I commuted.
It's not in the basement anymore?
Oh, actually, that one is like old. And it has like low accuracy at the moment. So I needed really good accuracy for my proof of like interferometric and SCT plus measurement, because I need some very good calibration. So I went there, and they were really nice. I mean, they helped me measuring with the CMM, and they showed great interest in my setup and concept. It was really fun experience. But still, like I spent 2 months there measuring CMM. But good thing about it was when I was explaining my experimental like result to the audience in the dissertation, there were so many questions. I mean, how do you know if they're really calibrate it or anything, but I could simply say, oh, I did CMM measurement for 2 months, and they just stop asking questions. So that made my other problem so easy at the dissertation. So yeah, I mean, after like spending many months later, I figure like it solved like more difficult problem for me. So all good.
Yeah.
Anyway, um, I keep like losing track, but let's get back to my result. So surprisingly, the measurement from interferometer and SCT plus, they matched really well. I mean, has to be one-to-one measurement. I mean, if I measure with this method and that method, they should give me the same amount of misalignment aberration. That's what I wanted. And that's what I got. I was like, really? I
Yeah.
did this
Yeah.
well? And even my advisor was so happy to see the result, even though I had to like do more analysis to get the error bar. But it was a clear one-to-one ratio
Hmm.
that we were seeing. And it was like, oh wow, I really did it.
Hmm.
And then I was like, ah, oh, yeah, I was really happy seeing that result. And like during dissertation, I keep saying, this is exciting, this is amazing, something like that, because that's what we all want as a researcher. I mean, providing such good proof based on my experiment. It was, it's something that you would always want. And even better is, like I mentioned, I also did some prediction work, like ZMX by ZMX modeling. Then I could actually predict the amount of aberration that I will get if I perturb this much of perturbation to my system. So
Hmm.
I can also do prediction. You know, science is all about making prediction.
Hmm.
If you can predict something based on your concept theory, then supported by your experimental data, that is what you dream of. I mean, being as a researcher. And I was able to do that. I was like, I wasn't really, I wasn't able to show my, excitement when first saw that, because like, it can't be right. There must be something wrong, because you can never trust yourself when you're a grad student, especially when you're all about to graduate. You are super tired and stressed a lot, and you know, but I was able to convince myself. I mean, even starting to see the error bars within the error bars, this is, I did it. I really did it. I mean, yeah, I almost gave up. I mean, actually, because of my health issue and COVID era and financial issues, those like realistic life problems can make you know, depressed and help cannot sustain your research life. Well, that also happened to me. I'm pretty sure it must have happened to have everyone. But finally seeing that result, it felt like, oh, I I was glad that I didn't give up. And
Hmm.
then finally here. And now I have to write dissertation in 2 months to to graduate and go to this company. And then yeah, this whole story. And then wow. I mean, yeah, that's all.
Yeah.
Yeah.
It's I think I used to talk about this a lot more when I was in or fresh out of grad school, and talk about it with other students a lot. But and we touched upon it lightly at the beginning, but certainly for any graduate students listening, or I think anyone considering graduate school, I think it's relevant. Um, it's a really hard process for any variety of reasons. I had my family here when I did it. Like I went to the U of A in Tucson. My family's in Tucson. Um, I was really bummed out. I got really depressed and thought I was really dumb. But I had my family to go talk to, and I mean, please correct me if I'm wrong, but I don't necessarily think that was the case for you, which I imagine makes it even harder to not have, whether it's family or whoever, even if you have friends that aren't in the graduate program, it can be really hard to convey like this is really tough, like for all sorts of reasons.
Yeah.
And it's very tempting, and it's not necessarily the wrong decision. I also want to make that statement for a lot of people to not finish a program. It might not be a good fit. It might not be a productive use of your time. And there's no shame in that. But that's not the case for you. It was a great use of your time.
Yeah.
I think the results are really amazing. I'll go back and quote in your simulation. So in your simulation, you simulated two test cases: a Ritchie Cretan and an aerospace doublet. And I think for the let's see, for the telescope system, you did 400 Monte Carlo trials. You kind of boiled this down to a singular number of misalignment.
Mm-hmm.
We don't have to get into details, but you did 400 trials, and it started with a average of 11 microns with a standard deviation of 5 microns of this misalignment number. And after the alignment process, the SCT plus, it was 10 nanometers with a standard deviation of 0.6 nanometers. No, pardon me, 6 nanometers. So like a dramatic improvement. And for the doublet, that number started with the numbers MM1 started with 1 to 15 microns and dropped to under 30 nanometers. So 1 to 15 microns to under 30 nanometers for all test cases. And of course, I didn't write down the actual physical tests that you set up, but the results, looking at them, were dramatic and extremely impressive. It basically matched your experiment or your simulation results, which is really incredible. I mean, that's like phenomenal alignment, and in a system that's fairly straightforward to set up. So yeah, congrats. I think
Thank
it's
you.
a really powerful method. Do you, I had, like I said at the beginning, I have a handful of unrelated questions. So before we move on, do you have any kind of final thoughts on the methodology, on kind of the future of the methodology, or I suppose the research experience in this project in general?
So right. Thank you for asking me that question. So this is just the beginning of something, right? New methodology, and I only showed the I mean, it's might be good enough for now, but eventually, if people really got interested in how to apply this methodology to their system, maybe I need a better you know methodology explained for different type of system, like for axial, I mean, non-axial systems, or for conjugate systems. I mean, I'm using conjugate to infinite conjugate system for now, but there are ways to modify this methodology for different systems. But probably I have to work on that if I can, so that it can be used for various fields. And also the one limitation that I can think of right now is that I've been using TV monitor to align 1 meter diameter telescope, but that means if it gets bigger than 1 meter entrance pupil diameter, then you need a bigger TV monitor. But I believe the largest one on market is like 85-inch in diagonal direction or something. So that means later, if they want to apply to bigger telescope system, they might have to do stitching or something, or have to use sub-aperture to find out the related misalignment aberrations. But those are still in question. I mean, what can be done for that kind of system is it's some things that can be studied. I mean, if anyone else want to continue this work, I would be happy. But but the good thing is that last year I went to a PIE conference and I met many people from Korea, like researchers from different institutes. And I met Dr. Yoon Jong Kim. He is from Korea's Space Science Institute. And then his specialty is alignment. And he showed great interest in my methodology. So I've been voluntarily having meeting with him and Daewoo since then. For now, we are having a pause because I just started my new job at KLA. But I'm willing to continue that meeting. I mean, it's a voluntarily work and it's for telescope alignment. It's a perfect example. It's going to be a perfect example. And that telescope is also non-axial symmetric system. So there's it's a good application and development to my methodology. So yeah, even though I started my career at industry, I'm still willing to, continue my study on this topic. And yeah, that's the thing that I wanted to mention.
Great. Yeah, I think that's very exciting to be able to continue to contribute to kind of the broader community's knowledge and science, even while you've gone into industry and are finding a successful career there. So yeah, again, when it is ready, I highly recommend to anyone listening that they read this. It's extremely well written. I keep on hitting upon that because that's a rarity for science publications. It's extremely well written and it's a very powerful method. If you are up for it and have time, I have entirely unrelated questions. They'll be pretty quick.
Okay.
Okay. The first one is, and I need to add, like my other questions that I've used in the past, these are shamelessly stolen from elsewhere. In this case, it's the University of Chicago. So the first question is, what surprising job have you had in the past?
Surprising job that I had in the past?
Yeah, so you're a doctor of optical science. You now work as I don't know, an optical engineer or something like that. So, if someone met you and they said, "Oh, Dr. Hyemin Yoo is a doctor of optical science, she's an optical engineer," what could you tell them was a job that you've had in the past that would surprise them?
Job that someone was surprised. No, actually, my life has been very tedious and boring, I think. But maybe if I can tell them that I had a chance to test 6.5-meter diameter optic, that would surprise them. I mean, not even common. I mean, that's really rare. In U of A, there are two labs that can make such large optics. And I was lucky to work at one of the optics shop, and that will surprise them. I mean, when I say 6.5 meters, they will be like, so how big is that? And then you will think about it and they will eventually get surprised. Oh, there's a way to make such large meter. And then I think that's one thing that I can think of that would most surprise people outside optics.
That's usually my go-to as well, is talking about the large mirrors that I've worked on. So the next one is, what would you be doing if you were not in the field of optics?
Oh.
And you could work in anything.
Not sure. I might have still in some other engineering or science related field, probably, because I have this goal personally that I want to grow old as a female engineer to motivate people, like young people. especially girls actually. In Korea, still like there are large a population of male engineers compared to female engineers. So it was when I first came to US, I felt like, relieved to see there are so many other students, like female students or female engineers in the field, showing great performances. So when I was like, younger, like 10 teenagers or something, I usually got motivated by, like famous scientists or researchers. But eventually, what helps you sustain, I mean, what helps you keep pursuing your study is actually the people that's surrounding you. I mean, not the famous renowned names. It's more of a like what you see in your daily life. Like I see, just people like from like various diversity, diversity and inclusion. That's something that I really like. That if you start to see people around you having different backgrounds in the same field and being in the same similar position, that actually helps you to, get encouraged more than, reading good articles about people from the past. so that's my main goal, like being a like female something in the future, like it's in engineering or science field. So even if I were not in optics, I think I might have been in different field of engineering or, science, I guess.
Great. Yeah. No, I think that's a great answer. I'll I'll have to rely on you to share this episode, um, because I don't know how large my Korean audience is. So I don't know how many young women in Korea this might reach. So hopefully I'll have to rely on you to share it there. But so the next question is, what do you hate that everyone else loves?
What do I hate? Everybody loves. Hate.
And you can't, I guess you can say that you don't hate anything,
hmm.
but I'm sure you hate something. And experimental optical setups would be a valid answer as well.
Oh, that's painful, but I didn't
Okay,
hate
okay.
it. Um, People love that probably dislike. Probably watching sports.
Yeah.
People love sports in the States. I mean, people here, they're crazy about basketball, baseball, football, like, but usually I go like, maybe not much. I mean, I used to like baseball, like, but not anymore. And it's probably because I forget rules quickly.
Yeah.
So that's something that I dislike, that probably everyone loves.
So what about the opposite? What do you love? Wait, yeah, what do you love that everybody else hates or dislike that everybody else or what or yeah, we don't have to use the word hate. We can just say dislike.
So, well, like, uh, I think I love the the desert in Tucson. That most people don't like the heat and dryness in Tucson. But I moved to Michigan now. Ann Arbor, city Ann Arbor, it's a beautiful place. I mean, I love this place too. I mean, green, humid, like very cool, like nice breeze out there. I see fireflies and lovely place. Um, but I often really miss the brown and heat, dryness in Tucson desert, seeing all the wild animals. If I bring this up to someone who knows Tucson, actually they are like, really? Maybe you need more time in Ann Arbor to enjoy this new environment that maybe you're, there's a thing called Stockholm syndrome or
Yeah,
something
yeah,
that you eventually like something that you should hate. But I don't know, I mean, I really love everything in Tucson. I mean, seeing all like javelina, bobcats, all animals actually, and birds, lots of birds, and like the sunset. Like there are things that you can love about, like if you can tolerate the heat.
yeah, yeah.
So I'll say I love the desert of Tucson, and there are people out there who dislike about them.
Yeah, I think that's a fair statement.
Yeah.
Uh I I'm of like mind to you. I really love Tucson, including the summer. But I think that if you polled the average person here, they would say that they hate it in the summer.
Yeah.
Okay, only three more questions left. I won't keep you here too long. What was the last book that you finished?
Oh, finished. Does it include scientific book
Sure, yeah,
or
that's fine.
um gosh, it's hard to say that I finished it because I only read some chapters of them. It's a shame. I mean, I used to read lots of books when I was like a teenager, but I haven't read that much. I recently started to go to library again, public library here. And then I borrowed one book called History of Plague or something, and it's a this journalist. He wrote like his experience about dealing with all the related COVID related news.
Hmm.
Like he was trying to warn people that it's really similar to like Spanish flu, and then he was like explaining like how he felt when people were like ignoring his like claim and everything, warning. But and then and I couldn't finish it because it takes time for me to, search words because I'm not a
Yeah, yeah.
English speaker. And then I wanted to renew the book. Actually, it was a very interesting book, but then the other person wanted to read that same book, and then I couldn't renew it. So I couldn't finish it, but that was the book that I read most recently. But I
Okay.
will finish it later. I mean, when
We'll
this
count
person is
we'll
done.
we'll count it as you will count it as valid because you're going to finish it. So
Yeah.
I think it counts. Um, well, this might, based on what you just said, this might be a bit of time ago, but maybe not. But what was the last book you recommended to a friend?
The last book that I recommended to a friend. Um, no, I don't have many friends actually. Just joke. I have many friends, but like I have very few valuable
Sure, yeah,
friends of
yeah.
mine. Yeah. Um, the thing is that we don't really recommend books to each other. But I got a recommendation from one friend. Is that okay to
Sure,
say
yeah.
that? I think it's called Tomorrow, Tomorrow, and Tomorrow or something. The most like one of the most like read like sold book in Amazon this year or something. Tomorrow, 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 and tomorrow, and tomorrow.
Hmm.
Um, it's a novel, and this title is from one of the Shakespeare. The I think it's Macbeth. I need to say. I will read this after I finish that history of play. So yeah, I haven't recommended any book to anyone. Sorry.
Yeah, yeah. Well, okay, that's still we'll count tomorrow and tomorrow and tomorrow. So I miscounted, which doesn't bode well for my capabilities as a scientist. I have two more questions. Can you share the best advice that you've received or the worst advice that you've received? Just one or the other.
As a science
I suppose it's really in general. I mean, it can
in
be in the
general.
field of science or it can be, in the field of life, whatever
Mm.
piece you think is most worth sharing that
One
you've
thing
received.
that okay, so one of the most valuable um One is, I think it's from my advisor, Matt. He told me an acknowledgement. There were many sentences, phrases that he used to, train me well. But there's one thing that I didn't mention there is because it's a long one. So I think it's that so smart people learn from their experience, but wise people learn from other people's experience is one thing that Matt taught me. So oftentimes, like even smart people, like they sometimes make mistakes and they learn from it. That's a good thing. I mean, everyone will have that experience in their life at some point, more than one time. I mean, many times. But if you could learn from other people's mistake, that's wise because, you know, you learn from it's like you having like wide perspective to see things, and then you learn from other people's experience, and that you didn't make any mistake, but you could still solve problems without wasting your time or something. I don't know. Like, so I thought that was one of the things that was most valuable um, advice that I got so far. And the worst one I can think of one. So there's always like this concern, like as a teenager, should I choose something that I like or should I choose something that I'm good at? It's like as a career path. There are people like tell you to, choose what you like because that way you can focus on and focus better. I mean, you can, sustain your your interest to this field, and then it's going to be your passion and enthusiasm that will help you, keep up the good work. But personally, I think either one is a good advice. I mean, because I have a good reason. I thought I liked astronomy, but there are so many factors around you that that might fool you. I mean, I thought I liked astronomy, but there were more details. I mean, I liked the principles of instruments related to astronomy, not astronomy itself. So when you when and it's hard to say like you will like this forever. Sometimes you ended up like disliking it because of many reasons. It's not bad. It's just that sometimes that's my experience actually. I thought I chose what I liked, but eventually I noticed that that decision was based on my, decision was from various factors. I mean, I wanted to like prove myself to someone. So I thought I pretended that I liked it a little bit. Maybe I was fooling my feelings. But later when I realized that, I was like so ashamed of myself. Like, and then I got so depressed that I was being like that. So like something or being good at something, it doesn't matter. I mean, at some point in your life will tell you. I mean, your life will eventually tell you um what you're good at and what you like. And it can be same for like, I mean, it can be the same item or it can be different, but it doesn't matter. What's important is that being diligent on your life. I mean, not just being like, so the background for choosing something that you like and something that you're good at is that you want to succeed eventually in the future. But that actually doesn't matter. I mean, your decision making at that point, sometimes it doesn't affect your future that much. It's just that trying to learn, like trying to know better of yourself is more important. Like, don't decide anything at that time. I mean, just enjoy your life and go out and talk to lots of people and friends or elderly people and like watch lots of news and learn what's going on in the world and see if you can like if your brain can like grow like wise and then eventually you'll notice that in your life you've already gained some good you have already won some good things that you can continue your life and that's more important. I mean that was the bad advice. I mean when I heard that told me you should choose whatever you like that that led me to something I won't say it's wrong, it's just all experience, but if I knew I could have known that it doesn't matter, it would have been better. I
Hmm.
think that's yeah, I it went too long. I mean, anyway, yeah.
No, I think that definitely resonates that, it's a fool's errand in high school. We ask kids to say like, well, what do you want to do for the rest of your life?
Yep.
Um, you don't know. You're
Hmm.
gonna change. Your interests are gonna change. So, um, but well, I want to give you the last word. Do you have any parting advice? If that's the worst advice you've had, do you have any parting advice for people, in the field of optics or considering the field of optics?
If anyone's want to study optics, that's a good choice. Please do it because we need more people in this field,
Uh,
obviously. And then uh, just I don't know, what should I say? Just don't be too harsh on yourself. I mean, it takes time, It takes time to be sure about yourself. I mean, everyone is smart, I know. I mean, everyone can be really smart and then passionate about something, and eventually they will like um there will be some point that they kind of regret for something, because of many reasons. But I would say just don't, you know, just be patient and see what your life will give you. And it takes time. Sometimes someone takes short amount of time to finish something, but some people it takes longer. But it doesn't matter once it's done. Later you will have another page in your life, and then you'll be able to enjoy that. And we have to live up to 100 years anyway. So and eat healthy and eat healthy and your body posture matters. So that's the advice that I have actually. Yeah.
well, great. My guest this week has been Dr. Hyemin Yoo. Hyemin, thank you very much.